All right, welcome back everyone. This is section number 5, the chain rule. In this video, our only goal is to practice the chain rule. We want to be more comfortable applying the chain rule, right, to a variety of problems. And that's not going to only include equations, which I know we've been doing a lot with equations, but we're also going to look at graphs and tables, right? So sometimes function information is given to us in these forms, and we can actually apply the chain rule in these cases as well. So we'll see a little bit of that. All right, so for this first example here, we do have some equations, and I want to push us to get a little bit faster at these things, but I would recommend go ahead and pause the video, and I'd like you to try to get the answers to these ones on your own. So again, I'm going to give you, a couple minutes. Again, pause the video, try to get as far as you can. All right, here we go. When I look at this function, right, we have to think about what is the inside function and what is the outside function, right? So in this case, for me, the outside function is stuff is being raised to the 5th power. So that is the outside function. Again, stuff being raised to the 5th power. So according to the chain rule, right, if I want the derivative of this, we're going to take the derivative of the outside function, right? So the derivative of the outside function is the 5 comes down, and then we're going to have stuff raised to the 4th power, right? But we leave the inside alone, right? So in the chain rule, the original chain rule up here, right, we take the derivative of the outside function, and then we leave the inside alone. This is still g of x. It's not g prime or anything like this. We leave the inside alone. So, okay, let's go ahead and leave that inside alone. In this case, it's 7x cubed plus 2x squared minus x plus 3. Then we multiply by the derivative of the inside. So the derivative of the inside is 21x squared plus 4x minus 1. And there's the derivative of the inside, and that right there is my final answer. No more simplification or anything like that. That's how I would expect you to leave it on a quiz or an exam. All right, for the second one, again, we want to take the derivative, applying the chain rule here. So we take the derivative of the outside. In this case, the outside function is tangent. So its derivative, remember we should have these memorized. This is a 2.4 thing. So the derivative of tangent is secant squared. Leave that inside alone, right? So we take the derivative of the outside, leave the inside alone. Then we multiply by the derivative of the inside. That's 6x plus 5. And again, there is my final answer. That's exactly how I would leave it on a quiz or an exam. Okay, so now that we kind of got the juices flowing with some equations, which we dealt with in the last video as well, let's go ahead and see with a table, right? I want to do a table of values here. Notice that we have the functions values, and then we're also given the derivatives values. And we do it for a variety of points. So we have it for x equals 1, for x equals 2, and for x equals 3. So I'd like to go ahead and figure out the derivative of h at 1, and h is defined by a composition of functions, right? F of g of x. Well, again, so I'm going to go ahead and apply the chain rule here. The chain rule says you take the derivative of the outside, f prime, leave the inside alone, and then multiply by the derivative of the inside. There we go. Now I want h prime of 1, so that means everywhere I see an x, I'm going to go ahead and plug in a 1. So I'm going to have f prime of g of 1 times g prime of 1. All right, and now I know when you take derivatives, right, you kind of work outside in, right? You take the derivative of the outside, leave the inside alone, right? You're kind of working outside in. But remember, when you evaluate compositions, you work inside out. So I'm going to go ahead and first figure out what is g of 1. So here is my g column, and I want g of 1. So that's going to be g of 1, when I plug in x equals 1, is 2. So this is going to be f prime of 2, right? Replacing everywhere I see a g of 1 with 2. Now g prime of 1. So I go to my g prime column, look at 1. So g prime of 1 is 6. So this is times 6. So notice I'm not done yet. In order to solve this problem, I need f prime of 2. So I go to my f prime column, and now I'm looking at x equals 2. So we get 5. So this is 5 times 6, which is equal to a total of 30. So this is how we can apply the chain rule when we're given a table of information. let's do it one more time here. I'm going to let you try to get as far as you can on your own for this one. Notice we've kind of switched around. Instead of f of g of x, we have g of f of x. And then we have a similar question here, find capital H prime of 1. So again, pause the video, try to get as far as you can, and then you can unpause it and see how we solve this. All right, and here we are. If you got the answer of 36, then you are spot on. Again, we're applying the chain rule here, but now we kind of have the order is somewhat backwards than what we had before. All right, so we have g of f of x. So when I take the derivative of the outside, it's now g prime. Leave the inside alone, f of x, then multiply by the derivative of the inside, and the derivative of the inside is f prime. Okay, so plug in 1, right, because we want the derivative at 1. So you get g prime of f of 1 times f prime of 1. And so we need to know what is f of 1 and f prime of 1. Well, you can go up here and you can find those. They're 3 and 4 respectively. So we're not done yet, right? We still need g prime of 3, since that was f of 1 was 3. So g prime of 3, we go over here and we see that it's 9. So we get 9 times 4, which gives us a total of 36. So again, this is how we can figure out these chain rule problems giving a table of information. Now, what about graphs, right? So now suppose I have these two functions, f and g, and so I'm defining, again, kind of similar to the last problem. We have little h is f of g of x, and then in this case I'm calling p kind of this opposite one, which is g of f of x. So I'd like to compute the following derivatives or explain why they do not exist. So let me go ahead and do the first one for you, and then I'll give you a chance to do the second one on your own before I spoil the surprise. So just as before, I need to use the chain rule. For part A, I have p prime of 1. So let's go ahead and calculate out p prime of x, which is going to be the derivative of the outside, leave the inside alone, then multiply by the derivative of the inside. We want the derivative at 1, so I'm going to go ahead and plug in 1 everywhere I see x. So I have g prime of f of 1 times f prime of 1. Okay, this is now where I need to start going over to the graph. Just like before I went over to the table, now I have to go over to the graph. So remember, let's figure out f of 1 here. F of 1 is going to be the function's height at the x value 1. So if I go here to the x value 1, and I go up to, how tall is f, right? So this one right here is g, so I keep going, there is f of 1. So at f of 1, it looks like the height here is 6. So f of 1 is 6. F prime of 1. So f prime, remember, the derivative is the same thing as the slope, right? So I want the slope of the function at 1. So I'm here, luckily this is a nice straight line, so I can calculate out its slope very easily, right? I don't have an equation, so I can't, actually take the derivative of anything. So I need to think graphically. So, okay, the slope of this function at 1 here, well, it looks like it's negative, right? Because it's decreasing. And if I do a rise over run thing, you can see as I do a run of 1, I do a rise of negative 1. Oops, I don't know what that's all about. And so the rise over run is going to be negative 1 over 1. So therefore, the slope there is negative 1. Okay, now the derivative of g at 6. So now I'm thinking about my g function, and I'm going over here to the x value 6. And now let's go ahead up to g. So it's right here. Remember, we don't care about the height. We care about the slope, right? Derivative is slope. So, okay, the derivative of g at 6. Well, let's see. If I do a run of 1, how much do I rise? Well, it seems like I'm going down 2. So in this case, the rise over run is going to be negative 2 over 1, which is the same thing as negative 2. So we go ahead and we multiply these together, and we get the result of 2. All right, let me go ahead and erase this, and you should pause the video, try h prime of 2 on your own, right? We're using a slightly different function over here. Try it on your own, get as far as you can. Again, pause the video, and then I'll spoil the surprise. All right, so maybe you saw it. This one has a little bit of a trick to it, right? It's not as straightforward as our previous one. So let me kind of explain where the hiccup is in this problem. So again, I went ahead and I used the chain rule to take the derivative of h, and then I started plugging in 2, right? So f prime of g of 2, and then h prime of 2, right? Plugging in 2 everywhere I see an x. So now, I'm at the value 2, and I go up to the g function, right? So g function is this one up here. There we are. And so we can see that the height, right, g of 2, what is the height at the x value 2 for the g function? Well, that's 6, right? So we have height 6 here. So I could go ahead and write 6. G prime of 2. G prime of 2, what is the derivative at this value? Well, you can see actually, let me maybe even erase this purple point and zoom in. And you can see actually at 2 there is this thing, a cusp, or right, kind of more informally, a jagged edge, right? So this is not differentiable at 2. If you were to take the left-hand limit and the right-hand limit, they would approach different things. And so therefore, the function g is not differentiable at 2. So, to some extent, maybe a little less formal, this is does not exist. So when you take anything and you multiply by something that doesn't exist, well, it can't possibly exist, right? So h prime of 2 in this case does not exist. And it's because the derivative at g, the derivative of g at 2 doesn't exist. So again, kind of if we went back to the statement here, compute the following derivatives or explain why they don't exist. So this one does not exist. Again, maybe I'll explain. Since the derivative of g at x equals 2 does not exist. All right, so that's how we can compute these things graphically. So we've seen tables, we've seen graphs, and now I'd like to get back to one more time around with our equations, right? So we have equations of functions, and I'd like to be able to quickly calculate the derivatives of these functions. All right, you've had a decent amount of practice with this. Again, I'd like you to pause the video, try this on your own, get as far as you can, and then we'll go ahead and unpause the video and see how you did. So pause it. All right, and I've done a little bit of work, but I haven't completely finished the problem here. For this first one, it helps to represent everywhere you have a square root. Remember, this is the same thing as raising to the 1/2 power. So I'm going to go ahead and rewrite this. Everywhere I see square roots, so I have x to the 1/2 power, I have the entire thing raised to the 1/2 power, and that helps me take the derivative using the power rule. So I notice that the kind of outside function is that stuff is being raised to the 1/2 power. So I take the derivative of that, right? So the 1/2 comes down, reduce my power by 1, and I leave the inside alone. Then I multiply by the derivative of the inside. So the derivative of x is 1, and the derivative of x to the 1/2, well, the 1/2 comes down, and I get x to the negative 1/2. And again, that's how I would leave my final answer. So if you got that, great job. All right. The second one is actually a little bit more straightforward. The outside function is stuff is being raised to the 100th power. So I take the derivative of that, right? The 100 comes down, and I have stuff being raised to the 99th power. Leave that inside alone. I emphasize this so much is because people have a tendency, I've seen plenty of students who take the derivative of the inside at this point, and they get the question wrong, unfortunately. So I really want to emphasize, take the derivative of the outside, leave that inside alone, then multiply by the derivative of the inside. So I get 4 minus 2x, and right there, that's my final answer. All right, and that's it for section number 5, the chain rule. Next time, I'm very excited. We're skipping right to section number 7, where we're going to be doing a lot of physics application problems, right? So we've been doing a lot of just memorize this rule, right? And it feels very disconnected to what are the derivatives actually used for. So I'm excited. Next section, we actually get to apply these things to some real-world problems. So we now have all these things, the quotient rule, the chain rule, trig derivatives, all this stuff. We finally get to apply it. All right, so I'm excited. I'll see you next time.